Welcome to today's video. In this tutorial, we'll explore how to generate novel radar waveforms using generative adversarial networks, GANs. Radar technology is evolving rapidly, and traditional waveform codes sometimes fall short in meeting the demands of modern systems like MIMO, multifunction, and cognitive radar. We'll show you how GANs, a type of deep learning network, can be trained to create unique radar waveforms with similar characteristics to existing ones. This is key for enhancing signal detection, reducing interference, and improving overall radar performance. Let's dive in. In this video, first we'll dive into GAN for waveform generation, where we explain why GANs are useful in creating new radar waveforms and how they address the limitations of traditional waveform codes. And we will cover next contents in future videos. Now, we're going to explore how deep learning, specifically using a type of neural network called a generative adversarial network, GAN, can be used to generate new phase-coded waveforms. This is especially important for modern radar systems such as multiple input, multiple output, MIMO, multifunction, and cognitive radar systems, which require unique and adaptable signal waveforms. Now, what exactly are phase-coded waveforms? These are radar signals that help us achieve good range resolution, meaning they allow us to detect objects at different distances with precision. At the same time, they ensure there's enough energy in the signal to detect the echo when it bounces back to the receiver. Phase-coded waveforms are particularly useful in situations where multiple radar systems are operating close to each other, helping reduce interference between them. However, the challenge arises because there are only a limited number of these code sequences in many radar code families like Frank, P1, P2, P3, P4, and Zadovchu. This limitation can be problematic as modern radar applications need a broader variety of waveforms. This is where deep learning comes into play. By using a GAN, we can train the network to generate new phase-coded waveforms that have similar ambiguity functions as the existing ones, but with more variety. The GAN works by learning the ambiguity function of existing radar waveforms. The ambiguity function helps us analyze a waveform's resolution and its ability to separate targets in both the range, distance, and Doppler speed domains. Once trained, the GAN generates new waveform sequences of a specific length, and these new sequences are evaluated by comparing their peak side lobe levels, PSL. PSL is a measure of how much interference or noise is present in the signal, and it helps us determine how effective the new waveforms are. We also check the uniqueness of these generated waveforms using correlation analysis to ensure they're different enough to be used in multiple radar systems without causing interference. In conclusion, using deep learning to generate new phase-coded waveforms helps solve the problem of limited radar code sequences. It allows modern radar systems to continue evolving and adapting by providing an endless variety of waveform options, essential for reducing interference and maintaining accurate target detection. A generative adversarial network, GAN, is a type of deep learning model that generates new data resembling the input training data. It's particularly useful when simulations are time-consuming or computationally expensive. In our case, we use GANs to generate new radar waveforms. The Wasserstein GAN with gradient penalty, WGNGP, is an advanced version of GAN designed to improve the stability of training and ensure high-quality generated waveforms. A GAN consists of two networks. Generator takes random inputs and creates synthetic data, waveforms, similar to the training data. Discriminator tries to classify whether the input is a real training waveform or one generated by the generator. For radar systems, the ambiguity function is crucial. It helps us evaluate a waveform's ability to detect objects by separating targets based on range and speed. This function ensures the new waveforms generated by the GAN have similar range and Doppler capabilities to existing ones, helping radar systems distinguish closely located targets efficiently. Let's break down the concept of the ambiguity function using an example of a Frank phase-coded waveform. In radar, the ambiguity function is used to analyze how a waveform performs in terms of range and Doppler resolution. The figure here shows the ambiguity function of a Frank phase-coded waveform with a sample length of 64. You'll notice a tilt in the ambiguity function. This is due to something called range Doppler coupling. Range Doppler coupling happens when the phase modulation of the waveform creates a link between the time delay and the Doppler shift. In simpler terms, the waveform's design affects how well the radar can separate objects in range and speed. Despite this coupling, Frank codes are still widely used in radar because they have some great features like good autocorrelation. The waveform can detect itself clearly and low side lobe levels, which means less interference from other signals. On the other hand, a random noise signal has a different ambiguity function, often described as having a thumbtack shape. This means it has a sharp peak at the origin and low values elsewhere, making it good for detecting targets at a specific point, but not very tolerant to Doppler shifts, meaning it struggles with targets that are moving. In this example, we use the ambiguity functions of various phase-coded waveforms to train the model and generate new radar signals that are suitable for different radar applications. By analyzing these functions, we can design waveforms that strike a balance between detecting range and speed based on the radar's needs. This allows radar systems to work efficiently in different environments by using customized waveforms. In this example, the ambiguity functions of signals are used as inputs to the discriminator network, but here's the interesting part. The discriminator doesn't actually look at the waveforms themselves. Instead, it focuses only on the shapes of the ambiguity functions to decide whether a signal comes from the generator or from the training dataset. So, what does this mean for the generator? Since the discriminator is only concerned with the ambiguity function shape, the generator has the freedom to create completely new and distinct waveforms, as long as the ambiguity function of these new waveforms resembles those in the training set. This allows the model to generate unique waveforms that are not present in the original dataset, while still keeping their key performance characteristics, like range and Doppler capabilities, intact. In simpler terms, the generator creates new waveforms using random noise as its starting input. The discriminator, on the other hand, is trained on ambiguity functions of phase-coded waveforms. The ultimate goal is for the generator to produce waveforms that have similar ambiguity functions to the ones in the training dataset, but are still new and unique. This process helps radar systems improve by introducing new waveforms that can perform well in distinguishing objects based on range and speed, while also being efficient for different radar applications. To train a GAN, train both networks simultaneously to maximize the performance of both. Train the generator to generate data that fools the discriminator. Train the discriminator to distinguish between training and generated data. Ideally, this results in a generator that produces convincingly realistic data and a discriminator that has learned strong feature representations characteristic of the training data. However, training GANs can often be unstable, and the generator can end up producing limited varieties of samples, a situation known as mode collapse. The Wasserstein GAN with gradient penalty, WGNGP, addresses these issues. It implements a unique loss function and a gradient penalty term that not only enhances training stability, but also improves the model performance. This makes the WGNGP a preferred choice for generating more diverse and realistic data. This example shows how to train a Wasserstein GAN model to generate novel phase-coded waveforms with similar ambiguity functions as those of existing phase-coded waveforms for a specific signal length. Thank you, and meet you in next video.